We're going to take a look at roots of complex numbers. So you've already had a look at doing operations on complex numbers, starting from addition, subtraction, moving on to multiplication and division. And previously you just looked at Moivre's theorem in finding powers of complex numbers. So the final step is to use Moivre's theorem as an extension to find roots of complex numbers. Just quickly remember the theorem for Moivre's theorem, which we write if z equals modulus of z cis theta, then z to the n equals the modulus of z to the n, and then cis n theta. Alright, so you should be able to recite that, and it is in the formula sheet as well if you need to refer to it. Now remember, this applies for n all rational numbers. Okay, so that rational numbers means that you can think of using that as to the power of 1/2. Alright, so an equivalent statement for writing roots would look like this. If z equals modulus of z cis theta, then the nth root of z will be the modulus of z to the power of 1 over n, and then cis theta divided by n. Okay, so we're dividing by n because when you multiply by 1 over n, that's another way of writing that fraction. Alright, so let's start off with a question that you already know the answer to. Like, what's the square root of 4? Okay, hopefully you tell me the answer is 2. Alright, don't get confused, it's not plus and minus 2, it's just 2. And that's because 2 times 2 equals 4. So you might argue that also negative 2 times negative 2 equals 4, but that's a different question altogether. So we can rewrite this in terms of an equation. We can say x squared equals 4. So what is x? Well, then x would be the square root of 4. And the square root of 4 is 2. Now when we're solving an equation, you'll need to understand that there's also a negative solution. This is where the plus and minus comes from. So you have to deliberately add a positive and a minus to show that there are two solutions. That's why you get plus and minus 2. Okay, that's not too bad. So what about solving the equation x squared equals negative 4? Okay, so you just started learning about complex numbers. So x should be the square root of negative 4. Do I need to put a plus and minus in front? Let's leave that for the moment and just figure out whether we need it at the end. So remember, the square root of negative 4 can be broken up in two parts. It's negative 1 times 4. Okay, so the square root of negative 1, we know this as I. So the answer must be 2i. Now we can think about this. Do we need the plus and minus? Yes, we do. Because what you have here is a quadratic equation. And knowing a quadratic equation always has two solutions means there's got to be two solutions. If I just left it at 2i, then I'm missing one. Okay? So the square root of negative 4 should give you plus and minus 2i. We can also solve this in a different way. So just quickly, we can have a look at rearranging that equation and writing it as x squared minus 4 equals 0. We can use factorization. Oh, sorry, it should be x squared plus 4. So we're going to use factorization, and when you think about it, we have to write it as x minus 2i, x plus 2y equals 0. And then we get our two solutions. Okay, so that's just a double check to show that the plus and minus is necessary. More about that later. So now we've looked at x squared equals 4, purely real. X squared equals negative 4, still real but in the negative. What happens if you have an imaginary value? How do you solve x squared equals 4i? Alright, let's use a similar process. So x equals plus or minus, and we're thinking square root of 4i. So we can break that up. We can have square root of 4 times square root of I. So we know what the square root of 4 is, which is 2. You might argue plus and minus, but I've already shown the plus and minus here already, so it's 2. But what is root I? Okay, so how do we figure this out? I mean, we know that I equals root of negative 1, so the square root of I must be the square root of negative 1, which is also known as the fourth root of negative 1. But what is that? How do we figure that out? So the problem here is that we started off writing our complex number in a Cartesian form. Let's use the power of de Moivre's theorem. De Moivre's theorem needs you to write the complex number in polar form. So if we redo this question by looking at it in a different way, you will be able to find these roots easily. So 4i, how do I write that in polar form? Remember, on an Argand diagram, where is it located? Okay, 4i is purely imaginary, so 1, 2, 3, 4, it's here. So my modulus is 4, but my angle, or my argument there, is pi on 2. So I can write this as 4 cis pi on 2. Now, we're going to do something that's not expected. We're also going to add cycles of 360 to our angle. More about why this works later, but let's just go with this at this point in time. So we're now going to add plus 2k pi. Okay, so the k means that you've got multiples of 2 pi. So if you really want to, you can also write that k is integer. So that means you can plus or minus. So what I'm doing physically is I'm saying that my argument is pi on 2, or I can add one whole cycle and say it is 5 pi on 2. Okay, or I can also go backwards. So let's just keep going with this. So to work out x, now I'm going to use the de Moivre's theorem. I'm going to take the square root of this whole expression. So I'm going to take the 4 cis pi on 2 plus 2k pi. Okay, raise that to the half. So the answer should be 4 to the half, which is 2. Okay, so square root of 4. And then the arguments all get divided by 2. Okay, so pi on 2 divided by 2 is pi on 4. and then I've got 2k pi divided by 2. Okay, so that's my answer in polar form. It's not easy to read though. I mean, how do I see that there are two solutions? Because remember, if we start off with a quadratic equation, then we should have two solutions down here. So what's with this k here? What we're going to do now is we're going to check out different values of k. We always start off with k equals 0. Now, the reason why is because it will make this term disappear. So this solution is called the primitive. So it's the first solution. And we do this because we only just want to use the argument on its basic form. We're not going to add any cycles of 2 pi to this. So if k equals 0, then the solution x equals 2 cis pi on 4. We can also expand this into Cartesian form so we can have a better understanding of what it looks like. We're used to writing our complex numbers with real part and imaginary part. So let's do this, and we'll simplify it by doing some work in our head. Pi on 4 is 45 degrees, so cos of 45 is 1 on root 2. So the real part will be 2 on root 2. And then similarly with sine of pi on 4, I will get plus 2 root 2i. Okay, so that's the solution when k equals 0. Now we're going to try moving around, so we add an amount of k. So if k equals 1, that means I'm going to add one lot of 2 pi to my answer. I'm going to get x equals 2 cis pi on 4 plus I'm going to get 2 pi on 2. 2 pi on 2. Which is really just one lot of pi. Okay, so we just double check that. Substitute 1 into there. The two 2's cancel each other out, so we just get pi. So this just turns into 2 cis 5 pi on 4. 5 pi on 4 is located in this third quadrant over here. Okay, so just do a little bit of working out. Hopefully you'll accept that this will be negative 2 on root 2 minus 2 on root 2i. Okay, so now we've got two solutions. We'll do one more and I'll just show you that this next one, when k equals 2, is not necessary. Okay, so when k equals 2, x will be equal to 2 cis pi on 4 plus 4 pi on 2, which is the same as adding 2 pi. Okay, I'm just substituting the k equals 2 into here. Now, if you just look at this, don't even think about expanding this and simplifying this. This angle here plus another 2 pi is literally the same as pi on 4, right? So you could write that this is 9 pi on 4, but you're wasting your time, okay? So it's really the same as 2 cis pi on 4, which is the same solution as back at k equals 0. So what's going to happen is you'll eventually hit this point where you're just cycling through the same solutions again, you're repeating them over and over again. What's more important is that you only need to have 2. So the ones that I've ticked here, they are the answers to the square root of 4i. So I'll just summarize this, okay? So therefore, x equals 2 solutions. You've got 2 on root 2 plus 2 on root 2i, or x equals negative 2 on root 2 minus 2 on root 2i. You could really say it's just the negative of 2 on root 2 plus 2 on root 2i. It's like the plus and minus. And that's exactly what's happened there. Okay, so using Moivre's theorem with a fraction power, which I'm using here as a square root, you can work out the square root of complex numbers. The next part you will look at is working out the roots of complex numbers that only have the modulus of 1. They're called roots of unity.